अच्छा, थर्मल पावर प्लांट के हवाले से कुछ चीज़ें आप ऐड करना चाहें तो आखिर में कर दीजिएगा, अभी मैं गो थ्रू करता हूँ। कुछ चीज़ें वही क्वेश्चन हुए तो आखिर में हम इसको इंटरटेन कर लेंगे। सबसे पहले क्लासिफिकेशन ऑफ पावर प्लांट्स है, तो अकॉर्डिंग टू टाइप ऑफ फ्यूल यूज्ड, तो स्टीम पावर प्लांट्स हैं फ्यूल की बेस पे, डीजल पावर प्लांट्स हैं, गैस टर्बाइन पावर प्लांट्स हैं, न्यूक्लियर पावर प्लांट्स हैं एंड दी हाइड्रो इलेक्ट्रिक पावर प्लांट्स। दीज आर द प्लांट्स। I will share in group also, okay. So just I will go through so classification of power plants. This is just based on the fuel used. So these are the 5 types, for example steam power plants, diesel, gas turbine, nuclear and hydroelectric power plants. Achha, according to the mobility of plants, stationary power plants and mobile power plants, and then there is a, according to nature of load, there is a base load power plants and peak load power plants. ठीक है, तो base load and peak power plant, there is another definition for base load. If the there is a formula I will show you. According to the nature of organization, central power plants are captive power plants. Captive means different distributed type power plants. और उसके बाद आप बेस पावर प्लांट्स की बात करें तो देयर इज़ अ कैपेसिटी फैक्टर ऑफ प्लांट, यू हैव ऑलरेडी आई थिंक सो मे बी गो थ्रू। तो उसमें इफ़ द कैपेसिटी फैक्टर इज़ ग्रेटर देन 57%, तो इट मीन्स दीज पावर प्लांट्स विल बी द बेस लोड पावर प्लांट्स. फॉर एग्जांपल, if you have what is the formula of capacity power plant, you can see here that capacity factor is the ratio of average power of the generating plant to the rated power. For example, average plant ratio of average power of the generating plant, for example we have installed 100 kilowatt, for example 100 megawatt power plant, for example we have installed. So this is the capacity, but he is generating that power plant is generating the rated power of 57 megawatt, for example. So 57 divided by 100, that will be 57. Its capacity factor will be 57. So in this way you can calculate the capacity factor. And this the other thing is 5000 full power hours working throughout the year. How you can calculate this 5000? For example, in calculator you will see that in one day there is a 24 hours. And 24 hours and for 365 whole the year, 365 days multiply by 24, so you will get what if you will want to calculate total hours in the year, how you will 8760, yes, 8760, these are the total hours in the year. So if the capacity factor is 57%, so 57%, how many hours this plant will be operating throughout the year? We want to calculate the hours. So 57% is the capacity factor, and total hours in the year is you will multiply 8760 multiply with 0.57. So how you will get, what's the answer? So it will be about 5000, nearly 5000 hours. So it will operate for about 5000. Okay. So similarly peak load power plants where the capacity factor is less than 23%, and same you can calculate. The next one is central power plants and then captive power plants. Central definitely we are the central power plants, for example Tarbela, Mangla and different plants, they are covering all the consumers. But captive, there are types run by the manufacturing or its local use. For some local power plants which our teacher, lab teacher Kashif Saab already demonstrated about different power plants in Faisalabad, something like Lahore, like that. And Rankin cycle, you already I think so cover this Rankin cycle, just we will go through this. There are the heat energy of the fuel is converted into mechanical work or power in the steam turbine power plants. The main 4 components, sir already covered this one, but let's recall. The first one is the boiler, turbine, condenser and feed pump. These are the 4 components. So here you can see the process 1 is the constant pressure heat addition in the boiler. So you can see here the constant pressure. Here you are entering the boiler need the heat, so you need the hot water. So QS, this is heat energy you have to supply to the boiler, and this is the input at one point. This is the thermal entropy, you can say, at point 1. This is the input and 2 is the output, and it is the constant pressure. 1 in and out. You will this is PV curve. P means pressure and V is the volume. So 1 to 2 will be the straight line. It means the pressure is constant at this point. And this second process is 2 to 3 process, that is called isentropic expansion in the turbine. Here you can see the pressure will also be increased. This boiler, the steam of the boilers which will be produced from the boiler, it will be fed to the turbine, and turbine there is the expansion. So here the volume will also increase, and also the you can see the pressure will be reduced in this process. So here the curve will be something like that, curve in this way. In this way it means the volume is also increased. Here you can see if the volume is in this point here, so now the last volume is this one, volume is increased, but you can see pressure was this one, and at this point the pressure is reduced. So this is the process number 2 to 3. And then there is a process 3 to 4, constant pressure heat rejection in the condenser. So now there is the heat this is the opposite of the boiler, you can see. So here the heat rejection, and this process you can see here, again the constant pressure, but volume will be reduced. You are just condensing the heat. And the last process, process 4 to 1, that is isentropic compression in the pumping process. So you need some external energy, WP, because you want to operate this pump, and this pump will fed this water again into the boiler just for heating process. So here you can see that the pressure, because you need the boiler, and boiler will you can say compression will occur and pressure will increase. So you can see here, if this point is the pressure is here, this P1, and you can see again the last stage, the first stage one, here you can see the pressure is increased. So this process is increased pressure, and here you can see only the energy we supplied here. This is the QS energy which is supplied to the boiler, and here you can see the energy or W work done by the turbine. This is the supplied, the turbine is supplying the energy, mechanical energy, because it is operating the generator. So this is you can see delivering, and this is we are absorbing or taking, and same some energy is taken by the pump. Okay, and here condenser, some energy condenser, you can see there is the you can say QR, this is QR. Okay, these two Q called, Q mean heat, and W mean work done. Okay, so these are the two work done, for example done by the turbine, and this is the work applied on the pump. Because it needs the. Now you can see here the pump work. For example, here pump work is WP. How you will calculate WP? H1 minus H4, because H1 is greater as compared to H4. So you will calculate H1 minus H4. And similarly, previous session process 2 to 3 process. Here you can see the WT. The work done by the turbine, or the mechanical energy which is supplied by the turbine. How you will calculate? This is H2 minus H3, because H2 is more compression, more pressure, and more energy, and here is the expansion. So H3 is less. You can say H2 minus H3. You will calculate WT. So in this way, and similarly QS, if you want to find the QS, so H2 minus H1, because H1 is cold water, or you can say the water which is not heated, and this H2 is the steam, you can say. So this H2 minus H1, you are finding these formulas. And next, these are the formulas. Now this Rankin cycle, you can say temperature and S entropy. TS diagram, if you want to find, here you can see here that from 1 point to 2. Here you can see this is the boiler, and then there is a second point, second to third, you can see the temperature is constant, temperature is reduced. 2 to 3rd process is the steam, because steam is expansion. So high temperature steam will drive the turbine, and then there is the steam will be, you can see the temperature of the steam will be reduced. So the second to third point is the turbine, and here you can see the temperature is reduced. And from 1 to 2 you can see the temperature is continuously increasing, because from the boiler you are entering the cold water, feeding the cold water, and the output of the boiler is very high temperature steam. So in process 1 to 2 there is the temperature increasing, and then from 2 to 3 there is the temperature is reducing. So then there is a condenser, and in condenser the temperature is constant, but you are extracting the all energy from the with the help of condenser, this unit extracting all energy from the water and heat exchanger, all process here, and cooling tower, everything. So here entropy will be reduced. You can see here from 3 to 0 there is an entropy, from here to here is reduced, but the temperature remain constant. So then there is a other processes 0 to 1, again there is a pump. This is pump. You will just compress the water, and then you will feed it to the boiler, and then there is a slight increase in the temperature. So this is cycle, and now you want to find the efficiency. So efficiency, to find the efficiency, just what is this? Net work developed divided by heat supplied in boiler. Net work developed means how much work you have delivered by the turbine. Actual what is the net outcome, what we want from this steam power plant? We need the work done by the turbine, or you can say mechanical energy supplied by the turbine to the generator to generate the electricity. So this is our net result. So this is the output actually, and input, what is input? We are feeding the water to the boiler. So the heat the supplied net heat supplied to the boiler, that is the input, and output is the net work done by the turbine. So this is actually the output over input. This is efficiency. So how you will find net work done? You can see here net work done. This is the turbine, because work done by the turbine, this is positive because it is delivering, minus there is a works you can say WP pump, because pump is taking some energy, because pumping just taking water from the condenser and it is feeding to the boiler. So this is energy, pump energy we have to supply. So this is the we will just subtract this pump energy from the turbine energy. Turbine is delivering power, this is more, and some energy will be utilized to the pump. So WT minus WP pump energy, this is the net energy, that will be the output. So the numerator in the efficiency formula, you will get this net energy. And the what is the net work done developed? Heat supplied in boiler, H2 minus H1, because heat supplied to the boiler is, you can say boiler, there is a boiler, H1 H2 minus H1, this is the QS. So it will be in the denominator, H2 minus H1. So now you can rearrange the figure. When you will rearrange the figure, for example in the numerator, H2 minus H3 minus H1 you will rearrange and you will get the formula. And if you will just skip, because the pump work done is very small, because the energy which is taken by the pump, that is very small, it is negligible. You can neglect, or you can put it as 0. So it means if pumping energy is very small, you can neglect this. It means output is only the net work developed by the turbine, that will be WT, and WT will be H2 minus H3. So you will get H2 minus H3 divided by H2 minus H1 is just the efficiency of the supplied heat supplied by the boiler. So in this way, simplified version of the efficiency you can also get here. So there again the Rankin cycle, you can see here, steam and water drum, you can see here, and then there is a point pressure P1 and enthalpy or heat H1 here, which is fed to the turbine. And then there is a pressure P2, because expansion occurred in the turbine, then it means pressure is not constant, that other pressure, that will be the less pressure, and that will, you can see the P2. And similarly the enthalpy will also increase heat H2 and not will be the same as H1. And the work done by the turbine will be H1 minus H2, we already discussed. Then there is a condenser where heat exchanger, you are entering, or this heat exchanger is utilizing the cold fluid, cold water or something like that, and hot fluid is coming out, and you can see the Q2, the energy here, Q2 is H2 minus H3, H2 here, and after condenser definitely the enthalpy or energy will be different. So H2 minus H3, this H3 will be different, but here you can see the P2. If P2 is here, before entering the condenser, there is a pressure P2, and here you can see we also already mentioned that this one is also P2. It means pressure remains same in this process. And then there is a other process, pumping. For pumping, H4 minus H3 we already discussed, and then there is a, after pumping there is a pressure that is called the P1. This P1 will be the same as the pressure fed to the turbine, because at this point P1 is this, and H4 heat definitely change. H1 your enthalpy will be different. H4 here it was H3 and H4, but P1 is the same as the pressure fed to the turbine. So this cycle is completed in this way. And now thermal power plants, here the practical you can see you can see the practical example here. There is a coal, for example, the thermal power plant operated with the coal. The input or the fuel is coal, for example. So here you can see the coal. There is a conveyor belt. Then conveyor belt, with the help of conveyor belt, you will just put this coal into the in this boiler or furnace. This is called furnace or boiler. Here the oxygen, or you can say the air and coal will burn. But before burning this coal, you will just it is called the pulverized pulverization. You will just yeah, in powder form. Very good. So you will convert this coal into powder form, and then this will be burned here, and the you can say the gases or the other smoke or something like that, this will be you will be out from here, from this tower. And then there is a water, you can see here there is a water, and this water will be fed to the this boiler, and then it will be heat up, and it will convert into steam, and then steam is going to, here you can see there is a steam turbine, and it will there is a some blades and something mechanism in steam turbine, and then it will operate the steam. And then there is a generator, electromagnetic generator, for example the magnets magnets, and there is a coil. So there is an electromagnetic process, and then generator will generate the electricity, and there is a transformer. If you want to transmit this to long distance, you have to step up to reduce the losses. So in this way you can use this one. Okay, and a large reservoir already there, because this is the main requirement. Reservoir will be more. And similarly the same process repeated here. You can see here something what is different. There is a coal storage. For storage reservoir, these are already mentioned that there should be a reservoir, and much tons of reservoir will be available, and their coal storage, you can see here the coal storage, and then there is a fuel coal, and it will go to the boiler, and then there is a steam, and there is a generator, and there is transformer, and then fed to the transmitted for the consumers. And there is a, from the steam there is a condenser, and condenser you can see there is a cooling tower which is connected with the condenser, and this with the help of cooling tower you are using this. And then there is a boiler feed pump, and you will again feed this to the economizer, you can say here. And then there is a air preheater. Air preheater is just before because there are very hot gases, and that hot gases also have the energy. We don't want to waste that energy, so you will these gases will be you can feed to the air preheater, and then this air preheater will extract all the energy from the hot gases, and then this gas will be you can say you will flow through the chimney, and then it will be exhausted. But that extra energy will be extracted with the help of air preheater, and that heat you can use again to hot the water, to you can say boil the water, or you can increase temperature of the water. And there is a ash handling plant. There is also ash handling plant. All the ash will be handled by this plant. So these are the simple. And here you can see the river or lake. There is a reservoir, and this cooling tower and condenser. Here we also have the reservoir. Extra water we need, this reservoir will be used. And there is a types of boilers. There are a fire tube, and the second one is water tube. So fire tube mean there are tubes. These are the tubes. Fire mean related with the tubes, and here water tube. These means these tubes are full of water, and here fire tubes mean these tubes are full of steam, or you can say hot gases or something like that. So it means fire tube mean the extra. This is the furnace, it will produce the hot gases, and these steam or hot gases will be flowing through these tubes. And water reservoir is you can say these tubes are placed inside the water reservoir, and this water will when will touch these tubes, hot tubes, it will convert into steam, and this outlet will be, we will get the steam, and this steam you will fed to the steam turbine. So this is the process. And water tube, this boiler type is you are just these tubes contains water, and water in and water out. So water in is the cold water and water out is the steam. So here the furnace and all the process here, furnace and so this boiler process here, the you can say you are burning the coal or something, whatever fuel you are taking. So it will when it will these tubes, because inside that burning process, so when the water will pass through these tubes, this hot energy, all the energy will be absorbed by this water, and water will convert into steam, and this steam will be fed to this steam turbine. So this water tube process is more efficient. This process or this type of boiler is more efficient as compared to the other one. And here you can see the comparison. This is the you can say fire tube. This is the fire tube boiler, and this is the water tube boiler. Water. This is the water tube boilers. And you can say fire tube boiler, the coal or fire tube water shell. That you can say the water shells available, and here you can see the coal shell or water tube. And then there is a 20 kilopascal. This is the pressure you can maintain here. But water tube, the second one, this you can attain 70 to 100 kilopascal pressure. So this more efficient. And low quality steam, you can say this is the low quality steam. It is high quality steam require, and here you can see we can get a high quality steam here in this process. And large construction, for this we need the large construction, but here small construction we need, because here are only the water tubes, and just it is easy to construct. And here the cleaning problem, there is also the cleaning problem, because you can see here cleaning process, this is more complicated as compared to this one, and easy cleaning. And this is the cost is high. Fire tube, this cost is high and this cost is low. So this was the just comparison. And now these types of steam turbines, for example, here you can see there are the buckets. For example, there is a steam turbine. We already discussed all the different types of turbines, Pelton, Francis and Kaplan or something like that. So here we saw that there are the buckets, or you can say there are the blades, and there is a nozzle, and when the high steam will be fed from this nozzle, it will strike the buckets, and the turbine will rotate, and the generator will be coupled here, and it will rotate the generator. So steam of types different, you can say the main parts of turbines is nozzle. This is the main nozzle, and then there is a runner. This is the runner, you can see here the moving part, and then there is a blades, the buckets are something. Every turbine has different shape or dimensions, Francis, Kaplan, everything different. So these are the buckets which will be connected with this runner, and then there is a casing, overall covering of the turbine, you can see here. So there are now the types of steam turbines, you can see according to the mode of steam action. According to the mode of steam action, there is an impulse turbine and reaction turbine. So in the impulse turbine we saw that there is a Pelton turbine, that is the impulse turbine, and in reaction turbine, that is Francis and Kepler was the types of reaction turbines. So you know this one. So this is according to mode of steam action. So here you can also see that this is the impulse turbine. Directly you can see from the nozzle you are putting this hot steam. This is example of water, but you can understand this to the buckets, and this is it will rotate. But in the reaction turbine, you can see here the water is in this, and then it will be out from different. For example, we saw that if water is in, and then there is a perpendicular water out, and due to that water out there is a reaction produced, and due to that reaction turbine will rotate. That is called the reaction turbine. All Francis, Kaplan, these are the reaction turbines. And then the types of single type of turbine, for example, according to the direction of steam flow. So direction of steam flow, there are also two types of steam turbines. For example, axial flow turbines, and then there is a radial flow. So you can see here, axial mean the flow is along the axis, you can see here, and radial the flow is, you can see the axis is this one, rotate, but flow is in this way. So perpendicular, you can see this is the radial flow. And the third phase of to categorize the turbines is according to the exhaust condition of the steam. The first one is the condensing turbine, and second one is the non-condensing turbine. You can read, for example, condensing turbine is the turbine in which the steam is condensed. When it comes out of the turbine is called condensing turbine. It produces large output with single unit. And non-condensing turbine, you can see the exhaust steam leaves the turbine at atmospheric pressure or low pressure. There is no condensation of steam takes place in the condensation, no process, but the output will be, you can see the exhaust of the steams will be at atmospheric pressure, no condensing process. And then there is a type of steam turbine, you can see here this fourth category to categorize the steam turbine is according to the pressure of the steam. So here you can see high pressure, medium pressure and low pressure. You can see the low pressure is turbines, it is categorized as the pressure range from 1.5 to 2 bar. And similarly medium pressure 2 to 40 bars, and greater than 40 bars, this is the high pressure turbine. So these are the categorization. And the fifth category to categorize the turbines is according to the number of stages. For example, single stage steam turbine, for example, definitely name mentioned that name shows that this will be single stage, and multi-stage steam turbine stages will be multiple. So just, and now the top thermal power plants in Pakistan, top 10, for example, here as you can see Hyderwala having the capacity of 157 megawatts. You can also search again, maybe the latest another high capacity available, but according to my information, these are the top 10 thermal power plants in Pakistan. So Fauji Hyderwala in 157 megawatts, Sai Power Limited Saiwal 229 megawatt, Angro Power Plant Gotki 227 megawatt, Lakhda Power Plant Jamshoro 150 megawatts, Tara Chemical Industry Faisalabad 40 megawatt, Angro Power Station Tharparkar 660 megawatt, Fauji Fertilizer Karachi 118 megawatt, Saiwal Coal Power Saiwal 1320 megawatt, Hub Coal Hub 1320 megawatt, Port Qasim Coal Karachi 1320. And the largest thermal power plant in the world is Taichung Power Plant. You can see here it is in Taiwan. Its capacity is 5788 megawatt. So this is the end of today's